Hi everyone, these are the solutions for your section 7.6 review guide. And so this is designed to help you prepare for tomorrow's quiz. And this quiz is going to cover exponential and logarithmic equations. So we're going to start off with exponential work, and then we'll transition into logarithmic work. And so this is the material that was first introduced Friday of last week and Monday of this week, and then we've been practicing it since. So the first kind of exponential equation that we want to be able to solve is the kind that comes from equating your bases. So what that means is that you're looking to identify what base could be used to represent both sides of the equations and what power is needed to get those bases to match. And so this is what you want to use as your technique when you see that there are two exponential expressions in a single equation instead of just one. So in the first problem, I have 2 to the 6x minus 1 equals 32 to the 4x plus 9. So seeing 2 and 32, I know that the base I'm going to be working with here is 2. Now the left-hand side is already in base 2, so I'm just going to copy it down as is. And then the right-hand side, I can take 32 and write that as 2 to the 5th power, because 2 to the 5th power becomes 32. And then I have a 4x plus 9 on the outside. At this point, my bases are equal, so I'm able to equate my bases and then solve for x. So the left-hand side will be 6x minus 1. The right-hand side will be 5 times 4x plus 9. So if I distribute that 5 in, I will have 20x plus 45. And then to combine like terms, I'm going to subtract the 6x over to the right-hand side. So 20 minus 6x is going to become 14x. Then, when I subtract this 45 over to the other side, I've got minus 1 minus 45 more, so that's going to become negative 46. Then, in order to solve for x, I'm just going to divide both sides by 14. And that's not going to give me a very nice decimal value if I take 46 and divide it by 14. So I would just leave it in the simplest possible fraction. So when you use the math frac option or the F to D option on a Casio, you'll see this as your simplified fraction. The corresponding decimal would have looked like this, 3.286, and so on. So since you would be rounding that, I would say go ahead and just keep it as a fraction. So that's our work here for number 1. For problem number 2, we're going to take the same approach, but we just have a little bit more going on mathematically because we want to equate the bases, but we have more than one expression going on. So I see 1/3, I see 9, and I see 27. So it's my recommendation that as soon as you see that 3 or you see numbers like 9, then you know that your base is going to be 3. So let's go ahead and rewrite 27 as 3 raised to the 3rd power. And then we bring along the 5x plus 3 exponent. 9 can be rewritten as 3 squared. And then I have this 2x plus 1 out here. And then that right-hand side, the 1/3 x, anytime I have 1 up top in a fraction, what that means is I had a negative exponent. And so to get from 3 to 3 down in the denominator, I would have 3 as a negative exponent. So I would have 1 as a negative exponent for 3. So that's going to be my setup here. So I'm going to go ahead and distribute all of these exponents. That way it's going to become easier for me to combine like terms and equate the bases. So this first term will become negative x. And then my second one, when I distribute that 2 in, it's going to become 4x plus 2. And then on the right-hand side here, I will end up with 15x plus 9. So on the left-hand side there, I have like bases that I'm multiplying, so I can just go ahead and add those exponents together. So negative x plus 4x is going to be 3x. So I have 3x plus 2 equals 15x plus 9. So now that I have 3 to some power equals 3 to some power, I only care about my exponents. So I can just go ahead and equate those exponents and then solve for x from there. So I'll have 3x plus 2 equals 15x plus 9. So let's subtract over this 3x here, and that's going to give me 12x. And then if I subtract the 9 over, I'll have negative 7 equals 12x. I can divide both sides by 12, and then 7 divided by 12 is going to be a repeating decimal, so I'm just going to keep it as a fraction. So these ones aren't working out, perfectly to nice round integer values, but that's okay. Just like any equation, we can end up with fractions, and especially once we get into logarithms, we'll see a lot of decimals that we're going to round. Next up, we are solving an exponential equation using logarithms. So here we have 3 times 2 raised to the x power equals 42. So when you're solving, you know you're going to be solving with logarithms when you just see a single exponential expression, not 2 equal to one another. And so your goal here is going to be to isolate the exponential expression, undo the exponent of the log, and then solve for x. So here, I'm going to divide both sides by 3. 42 divided by 3 gives me 14. So I have 2 to the x equals 14. Then to undo that exponent, I'm going to go ahead and take the log of the base of the exponent that I have. So log base 2 of 2 to the x equals log base 2 of 14. Log base 2 and 2 are going to cancel, and I'll have x equals log base 2 of 14. Then, if you have a newer TI, you can evaluate that expression directly in your calculator. If you have an older one or a scientific one or a Casio, we can just go ahead and evaluate this using the change of base formula, and then we're going to approximate to 3 decimal places. So log of 14 divided by log of 2, I get 3.807. And remember, you can check these by plugging back in. So you can do 3 times 2 to the 3.807 power, and that should be really, really close to 42. So I'm going to try that in my calculator. 3 times 2 raised to the 3.807. And so my calculator says 41.989, and so I'd round that up to 42. So that's my solution for 3. Number 4, really similar process that I'm going to work with here. I'll just have one more additional algebraic step, and then my base here is e instead of base 2. So I have e to the 4x plus 5 is equal to 60. I'm going to start this problem off by subtracting over the 5. So when I subtract 5 from 60, I have e to the 4x is equal to just 55. And then now that the exponential expression is isolated, I can undo it. And you're able to undo a natural base, so base e, using the natural log. So I'll take the natural log of e to the 4x is equal to the natural log of 55. Now remember, when we take the natural log of e, what essentially happens is the 4x can be brought out in front using the power rule, and then you have the natural log of e, but the natural log of e is just 1. So you have 4x equals the natural log of 55. So then, to solve for x, I just need to take the natural log of 55 and divide it by 4. And then same thing, we're going to get 3 decimals. So natural log of 55 gives me about 4.007. So when I divide that by 4, I get that x is equal to 1.002. And that's our final answer for number 4. For problem number 5, same kind of process. Again, I just have a few more algebraic pieces incorporated here, both at the beginning and then at the end as well. So I have 2 times 3 raised to the 2x minus 5 minus 4 equals 11. So I'm going to start by isolating the algebraic expression. So to do that, first I'm going to add 4. So that's going to give me 2 times 3 to the 2x minus 5 is equal to 15. Then I can divide both sides by 2, and that will give me 3 to the 2x minus 5 is equal to 7.5. So 15 over 2 is 7.5. Then from there, if I want to undo the exponential expression, now that it's fully isolated, I'm just going to take the log of whatever exponential base I'm working with. So I'm just going to bring this up here. I'll have log base 3 of 3 to the 2x minus 5 is equal to log base 3 of 7.5. Now when I do this, the log base 3 of 3 will cancel because the 2x minus 5 comes out in front from the power rule, and then log base 3 of 3 is just 1. So this expression is going to become 2x minus 5. And then over here, I'm just going to get a decimal approximation. If you can plug that into your calculator, that's fine. But if you need to do change of base, you'll take log of 7.5 over log of 3. So that value gives me 1.834. And then I need to add over the 5. So I will have 2x equals 6.834. And then I can divide both sides by 2. And when I do that, my final answer here is going to be 3.417. Next up, we have a quadratic exponential function. So these are the ones that are a good preview of what kinds of exponential equations you'll get started with in pre-calc. So you know this is a quadratic exponential equation. Oops, this one, I have the error that was originally in here. That should be 6e to the x, not 6x. So when I have e to the second power and also e to the first power with an x along with it, so 2x and x, that's when I know I'm going to have a quadratic expression. So this guy is e to the 2x plus 6e to the x minus 7 is all equal to 0. So I can factor this quadratic the same way I would just x squared. So I think about what multiplies to negative 7 that adds to positive 6, and that's just going to be a positive 7 and a negative 1. So I'll have my two terms broken apart like this. And then when I factor a quadratic exponential expression, it's going to break apart to e to the x instead of just regular x. Then I can solve each one of these separately. So I'll have e to the x minus 1 equals 0, e to the x plus 7 equals 0. So here, if I add over the 1, I'll have e to the x equals 1. And then if I try to take the natural log of both sides, the natural log and the e will cancel. X is equal to the natural log of 1, which is just going to be 0. And then if I go with this one, I'll end up with e to the x equals negative 7. But then when I try to take the natural log of both sides, I'll be trying to take the natural log of negative 7. So there aren't any solutions from this one. And the reason for that is that negative 7 does not work as a logarithm. Our negative values can't be evaluated with a logarithm. So my only solution here is going to be 0. Lastly, we have an exponential problem here. And this one is going to be the applications that we'll see with exponential functions. So most commonly, these are going to be population values for exponential growth or continuously compounded interest. You'll also see population models for different kinds of animals and bacteria and things like that. And then you can see exponential decay with things like radioactive emission or decreasing populations. So here it says you have deposited $500 in an account that pays 6.5% in annual interest, compounded continuously. How long will it take for your money to triple? What about quadruple? So when you have continuously compounded interest, that is when we are using this equation. A equals P e to the RT. So A is going to be your ending amount, and then P is the principal amount. R is going to be your rate, and T is going to be your time in years. So this specifically works for annual interest rates. So if we are interested in answering part A, our starting amount, the principal, is 500. We've got E, our rate is 6.5%, which becomes 0.065 as a decimal. We're solving for time. We want to know how long, that's the amount in years. And then for this to triple, that would mean it's equaling $1,500. So we're just going to solve through this equation. To do so, just divide both sides by 500, which means we'll have e to the 0.065t is equal to 3. And then from there, I just need to take the natural log of both sides to undo the exponential expression. So natural log of e to the 0.065t equals the natural log of 3. Now using the power rule, 0.065t is going to come out in front, and natural log of e will just be 1. And then I'll have the natural log of 3 over here. So to solve for time, I'll just divide both sides by 0.065. So natural log of 3 gives me 1.0986, and then I divide by 0.065. So I'll end up with a time value of about 16.90 years. So that's the amount of time for it to triple. Then if I want to solve through to quadruple, I can either, for part B, begin at the equation that I had up here. So I can start back with this and think through what it would take to make $500 quadruple. Or what I can also do is notice that when I worked through the triple equation, I just ended up with the e raised to the RT equal to the amount, the factor that it takes to multiply. So tripling would be 3, quadrupling would be 4. So I can set this up as e to the 0.065t equals 4, and then I can just pick up the equation solving from there. So I kind of saved myself a step. Then I need to use the natural log, and I'll take the natural log of 4 over here. Again, natural log and e will end up canceling to 1, and I'll have 0.065t equals the natural log of 4. I can divide both sides by 0.065. And so when I plug this in, natural log of 4, I get 1.386, divide by 0.065, and I end up with 21.33 years. So this is the same approach that you will take to solve any of your compound interest or exponential growth model problems. Next up, we are diving into our logarithmic equation work. So problem number 8 says to solve the following log equation using exponentiation. Exponentiation just refers to the process of undoing a log by making the corresponding exponent base the base and then the log the exponent. So here our first equation says 2 times the natural log of x is equal to 7.8. So just like how we want to isolate an exponential expression when we solve those, we also want to isolate a logarithmic equation when we solve through those. So here I'm going to start this problem by dividing both sides by 2. So the natural log of x is equal to 7.8 over 2, which is the same thing as 3.9. So if you think about the natural log, that's the same thing as log base e. So if I want to undo this with exponentiation, I'm going to make both sides exponent bases of e. E and the log base e will cancel out, and x is equal to e to the 3.9 power. So when you plug this in, remember you can find e from using your second division button. And so the value that I get here is 49.402. So next up, very similar process where we're going to solve using exponentiation. And so we just want to make sure we get that logarithmic expression fully by itself before we make it a power. So I'm going to start this one off by adding 5 to both sides. That's going to give me 3 log base 4 of x plus 2 is equal to 15. Then from there I can divide both sides by 3. So log base 4 of x plus 2 is equal to 5. Then to undo the log base 4, I need to make both sides powers of 4. The 4 and the log base 4 will cancel one another out, and I'll end up with x plus 2 equals 4 to the 5th. So 4 to the 5th is kind of a big number. It's 1024. But then this one's going to work out to be a nice even number, because if I subtract over the 2, I will end up with x being equal to 1022. So we walked through how to plug back into an exponential equation, but let's also do that with a logarithmic equation. So if I want to confirm my answer is correct here, I'll have 3 log base 4 of 1022 plus 2 minus 5 equals 10. So 3 log base 4 of 1024 minus 5 equals 10. And so remember, you can evaluate this using change of base, where you would say log of 1024 over log 4 if you don't have the log capabilities on your calculator. If you do, just plug it in exactly as is. And so when you do that, log of 1024 divided by log of 4, you should get 5. So then you ask yourself, 3 times 5 is 15, minus 5 is 10, 10 equals 10. We found the right solution. We're good to go. For problem number 10, this one, again, we're just solving with exponentiation, but we just happen to have a quadratic equation inside of the expression, so we'll have one additional step or 2 additional steps at the end. So I'll begin by isolating the log, so I'll subtract over 2 here, and I'll have 5 log of x squared minus 1 is equal to 10. I can divide both sides by 5. 10 divided by 5 is going to give me 2. So I'll have log of x squared minus 1 equal to 2. Now when a log is not indicated as to what base you're working with, we assume we are using the common log, which is base 10. So if it's not written, assume that you have a 10 there. So if I want to undo a common log, I need to make both sides powers of 10. So this will be 10 here and 10 here. The 10 and the log base 10 will cancel, and I'll be left with x squared minus 1 equals 100. So then, to solve for x, I need to add over the 1. So I'll have x squared equals 101. I'll square root both sides. And then when I take the square root of 101 and round to 3 decimal places, I end up with 10.0, and that's going to be 50. Now, I'm taking a square root, so it's going to be plus or minus that value. So I'll have plus or minus 10.050. All right, on your back page, we get started solving logarithmic equations that involve your properties of logs. So here you want to make sure that you feel confident with your multiplication property, your division property, and your power property. So looking at problem number 11, we have log base 6 of 3x plus 14 minus log base 6 of 5 equals log base 6 of 2x. So before you go about combining your logs, you just want to make absolutely sure that the logarithms are the same base. So we can only combine logs when the bases match. Now for this section, that's going to happen, but with future math, you'll find that there are logarithmic equations you can solve where you have different values of log bases. So just keep your eyes out for those. Looking at this negative sign over here on the left, I can condense those 2 logs into a single expression using division. So I can say log base 6 of 3x plus 14 over 5 is equal to log base 6 of 2x. Now once I'm in the situation where I have 2 logs with the same base equal to one another, that's really similar to having the same bases of exponents equal to one another. So I can get rid of these logs by exponentiating with the same base, and then I just end up equating what is inside of the logarithm. So I have 3x plus 14 over 5 equals 2x. I'm just going to multiply this 5 over on both sides. So that's going to give me 3x plus 14 equals 10x. I can subtract over this 3 here. And when I do that, I get 14 equals 7x. So my next step is just to divide both sides by 7. And when I do that, x is just equal to 2. So I only have a single answer here. Next up with problem number 12, I'm just looking at, do I have the same logs? And if so, what properties can I combine so I just have a single log equal to a number or a single log equal to another log? So here I have natural log of 5x plus natural log of x minus 1 equals 2. So since there's addition going on, I can combine these logs as a single log with multiplication. So I'll have natural log of 5x times x minus 1. Oops, I kind of overused parentheses there, but that's okay. Equals 2. So then if I want to undo a natural log, I need to be working in base e. So I'm going to make this side base e and this side base e. So these are going to cancel out, and I'll be left with 5x times x minus 1 equals e squared. So then, in order to solve for x, I'm going to distribute in. So I'll have 5x squared minus 5x equals e squared. And then to solve a quadratic, I'm going to subtract over that e. So I'll have 5x squared minus 5x minus e squared equals 0. So guys, we end up with this quadratic. If I want to solve through this quadratic, I'm going to have to use the quadratic formula because values with e are not going to factor. Now, that's definitely not my favorite thing to do. I really don't like it when they work out that way. I'd rather have nice numbers that are going to factor, but this is good practice for Chapter 4 on your final where you will have to use the quadratic formula. So let's go ahead and plug in. My negative b is going to be 5 because negative negative will be positive 5. And then the square root of b squared, my b value is negative 5, so squaring that will give me 25 minus 4ac, so minus 4 times 5, and then my c is negative e squared, and all of that is over 2a. So that's going to be 2 times 5, which is 10. So this will be 5 plus or minus the square root. I'm going to go ahead and get a decimal approximation of that value. So 25 minus 4 times 5 times negative e squared. I get 172.781 divided by 10. And so if I take the square root of that, I end up with 13.145. So 5 plus or minus 13.145 over 10. So if I take 5 and add it to 145, I get 18.145. Dividing that by 10, one of my solutions that I get is 1.81, and let's round that up to 5. And when I subtract, I end up with negative 8.145, and I divide that by 10, and so I get negative 0.815. So remember, anytime you solve through logarithmic equations, you always want to check for extraneous solutions. Normally, this kind of work is going to give you much nicer output x values. If we could factor, we would end up with nice and easy x's to look at, like we've done in the past. Here, if I just take a look back at my original log, I can tell that plugging in the negative value here or here would give me a negative log. So that means that this solution is extraneous. So my only final answer that I'm going to report is 1.815. So I apologize that that one is not super fun, and I will do my best to give you one that factors a little bit nicer tomorrow. But if not, it's good practice with the quadratic formula. Okay, you guys, last longer log problem is this one that involves both the power rule property and some division. So we have 2 times log of the square root of x minus log 2x minus 3 equals log 3x minus log of x plus 11. I think I might have said multiplied somewhere in there. I just meant what was inside of the log argument. So what I want to do first is to go ahead and use the power rule here. And when I do that, I'll end up with the square root of x squared, which is just x. So I can rewrite this as log of x minus log of 2x minus 3 equals whatever I had on this side. So log of 3x minus log of x plus 11. Now, because there is subtraction on both sides, I can write each side individually as division. So this is going to become x over 2x minus 3 if I put it inside of a logarithm. And then this side is going to become 3x over x plus 11. Now here I have 2 common logs equal to one another, so what I can do is make both sides exponents of 10 because common log is base 10. The 10s and the logs are going to cancel, and then I'll have x over 2x minus 3 equals 3x over x plus 11. So now I have a rational equation to solve, but unfortunately I've got a little bit more work to do because I need to cross multiply. So first up, I'm going to take the x and multiply it by x plus 11. So let's kind of give ourselves some room up here to do that. X times x plus 11. And then I need to distribute 3x times 2x minus 3. So my right-hand side is going to be x squared plus 11x. And then this side is going to be 3x squared minus 9x. So let's go ahead and bring that all over to one side. If I subtract over the 6x, I'll end up with negative 5x squared. And then if I add over the 9x, I'll have plus 20x is equal to 0. So thankfully, I'm not going to have to factor this quadratic into two different linear terms. I can just bring out negative 5x, and then I'll be left with x minus 4. So from this piece, my solution will be 0. From this one, my solution will be 4. So looking back at my original expression to see if one of these is going to be extraneous, x equals 0 is not looking so good, because if I try to plug that in here, I'll have 2 times 0, which is 0. 0 minus 3 is going to give me a negative number. So this guy is extraneous, and that means my only real solution is x equals 4. So problems 12 and 13 are probably the most challenging kinds of problems we can encounter, and certainly having to use the quadratic formula on 12 did not make it any better. But please let me know if there's any way I can help out with those too. The very last problem here is just to give you a sense of where you could see logs used in application. We're really focusing on emphasizing our exponential applications, but this one is just a good practice problem. So it tells us the retail sales in billions of Amazon, the online company, beginning in 2000 could be modeled by the following equation. Y equals negative 550 plus 234 times the natural log of t, where t is years after 2000. During which year did, or when will, the sales reach 104 billion? So it tells me that y represents the sales in billions, so I can just go ahead and plug 104 in for y and solve for t from there. So I've got negative 550 plus 234, natural log of t. So if I add over that 550, 104 plus 550 is going to give me 654. So 654 equals 234, natural log of t. So I'm going to divide over the 234. And then 654 divided by 234, I can give myself 3 decimal places. 2.795 equals the natural log of time. And then to undo the natural log, I just use base e. So my time value is going to be e to the 2.795 power. So e raised to that value will give me 16.361 years. So if that's years after 2000, what that means is right around the year 2016 is when Amazon's going to pass that sales mark of $104 billion. So that's our work with logarithms. I'm going to recommend a few additional textbook problems that I think would be useful to practice if you're looking for just a little bit more review before tomorrow. So you'll have your multiple choice quiz on Friday, and then Monday will be our last review day before finals begin. So just remember that there are ongoing reviews after school for each of the individual chapters. That way you can see all of the material from chapter 4 up through chapter 7 and chapter 8 for this semester's final. So please let me know if you have any questions. Otherwise, this is it for our new content for the year.